Hello everyone. Today I will be presenting my project on a traffic light controller using the 8085 microprocessor. In this project, I have interfaced the ET-TLC traffic light module with the 8085 using the 8255 programmable peripheral interface. The system controls multiple LEDs to simulate real-world traffic signals, and timing is managed using software-based delay routines. Along with basic implementation, I have also introduced some innovations like yellow light blinking mode and adapted delay control, which make the system more realistic and flexible. So let me first explain what the ETTLC module is. The ETTLC is a traffic light simulation module that mimics a real-world intersection using red, yellow, and green LEDs. Each LED represents a specific signal. Red indicates stop, yellow indicates transition or get ready, and green indicates go. Now, instead of manually controlling these LEDs, we interface this module with the 8085 microprocessor using the 8255 PPI. This allows us to control the LEDs programmatically by sending output signals from the microprocessor. Now, coming to the objective of this experiment, first, to understand how traffic light systems can be simulated using LEDs. Second, to learn how the 8255 PPI is used for output port interfacing. Third, to write 8085 assembly program to control the sequence of signals. Fourth, to implement delay routines, which are very important because they control how long each signal stays on. And finally, to understand how microprocessors can be applied to real-world systems like traffic control. Now let's look at the hardware components used in the system and how they work together. At the core, we have the 8085 microprocessor, which acts as the brain of the system. It executes the assembly program and generates control signals based on the logic we write. However, the 8085 cannot directly control multiple output devices efficiently. So we use the 8255 programmable peripheral interface, which acts as an interface between the microprocessor and an external hardware. The 8255 provides three ports: port A, port B, and port C, each of 8 bits, giving a total of 24 input-output lines. In this experiment, these ports are configured as output ports to control the LEDs. The LEDs represent the traffic signals red, yellow, and green. For multiple directions like north, south, east, and west, additional LEDs are used for right-hand indicators. Finally, all connections between 8255 and traffic light module are made using a 26-pin FRC cable. Proper alignment of pin 1 is important to ensure correct signal mapping. So overall, the 8085 sends the data, the 8255 transfers it, and the LED displays the traffic signal accordingly. Now I'll explain how the LEDs are actually controlled using the 8255 ports. Each pin of port A and port B is connected to one specific LED on the traffic module. So essentially, each bit directly controls one light. Starting with port A, which is mapped to address 00H, PA0 controls R1, PA1 controls G2, PA2 and PA3 controls Y1 and Y2, PA4 controls G1, PA5 controls R2. PA6 and PA7 control right-hand indicators RH1 and RH2. Similarly, port B at address 01H controls the remaining LEDs. PB0 and PB1 control R3 and R4. PB2 and PB3 control Y3 and Y4. PB4 and PB5 control G3 and G4. PB6 and PB7 control RH3 and RH4. The important idea here is that we send a binary value to a port. Each bit in that value turns a specific light on or off. For example, if a bit is 1, the corresponding LED turns on. If it is 0, the LED remains off. To enable this, the 8255 is initialized using a control word 80H, which configures all ports as output ports. Port C is also configured as output, but is not used in this experiment. So overall, by careful choosing the binary pattern we send to port A and port B, we can control the entire traffic signal sequence. Now, I'll explain how the actual traffic signal sequence is implemented using the port values. In the system, traffic is controlled in two directions, north-south and east-west. At any time, one direction moves while the other waits, and then they alternate. This sequence is implemented in 8 steps, where each step corresponds to specific binary values sent to port A and port B. Each hex value here represents an 8-bit pattern that turns specific LEDs on or off. So step 1 is initially the port A is 21H and port B is 30H. This turns on red lights for north-south and green lights for east-west. So north-south traffic stops and east-west traffic moves. In step 2, port B changes to 0CH, turning on yellow lights for east-west. This indicates a caution signal, vehicles prepare to stop. Then port B becomes C3H, which turns on red lights for east-west along with right-hand indicators. Now east-west traffic is fully stopped. Now step 4, both directions briefly show yellow using 0CH for both ports. This acts as a transition phase before switching flow. Then port A becomes 12H and port B becomes 3H. This turns on green for north-south and red for east-west. So now north-south traffic starts moving. Next, yellow lights for north-south are turned on, indicating caution before stopping. Then, red lights for north-south turn on, along with right-hand indicators. Now, north-south traffic is fully stopped. Finally, both directions again show yellow briefly, and then the sequence loops back to step 1. Now, I'll explain how timing is controlled in the system using delay subroutines. Since the 8085 does not have built-in timing functions, delays are generated using software loops. The idea is to repeatedly execute instructions in a loop so that total execution time creates a visible delay. Here, delays are implemented using nested loop counters. We use register B as a counter where we load a value into B and decrement it repeatedly until it becomes 0. Inside this loop, we call a smaller delay routine which provides a base delay. By repeating this multiple times, we get a longer total delay. So, in delay 1, we load register B with value 0CH, which is 12 in decimal. Each loop iteration gives approximately 0.5 seconds of delay, so total delay becomes around 12 into 0.5 equals to 6 seconds. This longer delay is used for main signals like red and green, where vehicles either stop or move. Now, in delay subroutine 2, we load B with 03H, which is 3 in decimal, so total delay becomes around 3 into 0.5 equals to 1.5 seconds. This shorter delay is used for yellow signals, which act as transition or caution phases. Now, let's look at how this is implemented in assembly. The MVI BXX loads the loop count in register B. Call delay calls a base delay routine. DCRB decrements the counter. JNZ repeats the loop until B becomes 0. RET return backs to the main program. So essentially, this loop keeps running until the required delay is achieved. Now, I'll explain the overall program flow of the traffic light controller. This flow shows how the microprocessor continuously controls the traffic signals step by step. First is initialization. First, we initialize the 8255 PPI. We load the control word 80H into the accumulator and send it to the control register using MVIA 80H out 03H. This configures all ports A, B, and C as output ports. Step 2 is output signal pattern. Next, we send specific binary values to port A and port B. These values correspond to a particular traffic condition like red, yellow, or green in different directions. Each bit in the output controls one LED as defined in the port mapping. Step 3 is the delay. After setting the signal, we call the delay subroutine. This ensures that signal stays on for a visible duration, longer for red or green, and shorter for yellow. Next sequence step is the step 4. Then the program moves to the next step in the sequence when a new combination of LEDs is activated. Step 5 is looping. Finally, after completing all the steps, the program jumps back to the start using jump start. This creates a continuous loop, allowing the traffic signal to run indefinitely. So, along with the basic traffic control system, I implemented a few modifications to make the system more realistic and flexible. First, I implemented a yellow blinking mode, which simulates caution signals used during low traffic conditions like nighttime. Instead of keeping the yellow LED continuously on, I made it blink on and off repeatedly. This is implemented by turning the yellow light on, calling a delay, turning it off, calling the delay again, and repeating this in loop. So instead of increasing the duration, we are actually creating a blinking effect using alternating on-off states. In assembly, we send the yellow LED bit pattern using out, then count delay, then send 00H to turn it off. Call delay again and loop using J and Z. This creates a visible blinking signal. So this is not longer yellow, it is a time-based toggling of the LED state. Innovation 2 is the adaptive delay. Second, I implemented adaptive delay to simulate different traffic conditions. Instead of changing hardware, I modified the delay values in software. Originally, delay 1 was 0ch around 6 seconds, delay 2 was 03h around 1.5 seconds. I increased these values to 18h for longer red or green duration and 6h for longer yellow duration. This allows us to simulate heavy traffic, longer green-red durations, and safer transitions, slightly longer yellow duration. So the system becomes configurable purely through software without changing any hardware conditions. So these modifications show that the system is not fixed, it can be extended and tuned depending on real-world traffic conditions. Now, let's look at the implementation of these projects and innovations in the lab itself.
In this experiment, we needed to implement a traffic light control system using 8085 microprocessor. So a traffic light system controls vehicles movement using three lights. Red is stop, yellow is wait, green is go. We needed to establish this particular sequence by which we can control the pathway of vehicles on 4 roadways. So this is the opcode which we put in, and after that we can see that after executing the code we can see the established sequence of the traffic light controller. Here the one pathway is green and then the other pathway becomes green because the vehicles go in that way. Then it becomes yellow and then red and then the other pathway becomes green. So this way the vehicle traffic is controlled. Now in this next mode I have achieved a yellow blinking mode by which the traffic will get a signal to like slow down but not at all stop. We achieved this by reducing the delay of the yellow and thus it is giving a signal of blinking. It is used in many real world applications. Now, as we saw about the traffic light controller, one innovation we can do as some traffic can take more time to like leave, so we increase the delay time by changing the opcode, and now the traffic lights are on and off for the longer time period, so that pedestrians can move when red light is on for longer time and vehicles can move when green lights are on for longer time.
Now, I'll briefly explain how we actually implemented and tested this system on the hardware. First, we connected the ETLTC traffic light module to the 8085 trainer kit using a 26-pin FRC cable. It is very important to ensure that pin 1 of the kit aligns with pin 1 of the module. Otherwise, the connections will be incorrect and the system may not work properly. Next, we provide power to the system. The module requires +5 and ground, which can either be taken directly from the trainer kit or from an external regulated supply. Stable power is important because incorrect voltage can lead to unpredictable LED behavior. Step 3 is then we load our assembly program into the memory. We manually enter the program starting from memory address 2000H using the kit keypad based on the opcode listing. This step ensures that the microprocessor executes our exact instruction sequence for controlling LEDs. Finally, We execute the program and observe the LED outputs on the traffic module. The LEDs follow the defined sequence of red, yellow, and green signals along with implemented delays. So overall, this procedure ensures correct hardware interfacing, program execution, and real-time observation of the traffic signal behavior. Now, coming to the results of our implementation. We observe that the red LEDs for either north, south, or east-west directions remain on for approximately 6 seconds, representing the stop condition. The yellow LEDs act as a caution signal and blink for around 1.5 seconds, indicating transition between stop and go states. This blinking behavior was one of our modifications to better simulate real-world traffic signals. The green LEDs remain on for approximately 6 seconds, allowing traffic flow in that direction. The entire signal sequence runs in a continuous loop without interruption, controlled by our assembly program. This system can be further enhanced by integrating traffic density sensors, IoT-based control, or FPGA-based real-time optimization. This would allow dynamic traffic control instead of fixed timing. Now, from this experiment, we can conclude that we successfully interfaced the 8085 microprocessor with the 8255 PPI, demonstrating hardware-software interaction. We simulated a real-world traffic signal system using LEDs. We implemented precise timing control using software delay subroutines. We also introduced innovations like yellow blinking and adaptive delays, improving realism without modifying hardware. This shows that even small software level modifications in embedded systems can significantly enhance real world functionality without increasing hardware complexity. Thank you.